Okay, yeah, so thanks for coming. So today we have Katherine Perry from Soka University of America. Yeah. In California, in US. And she's visiting here for 2 months. And she will talk about symmetry breaking, right? Please.
All right, thank you so much. Thank you everyone for coming. Yeah, thank you for letting me visit as well. Okay, yeah, so like Sanyal said, I'll be speaking about symmetry breaking in trees. And this is joint work with Calum Buchanan, Peter Dankleman, Isabel Harris, Paul Horn, and Emily Rivett-Carnac. And this was started at a research workshop hosted by the Masamu Advanced Study Institute in Pretoria, South Africa this year, the year that this project is from. But each year it's at a different place in Southern Africa and is meant to facilitate research collaborations between the US and Africa and at various levels of career. So at the time of this, Calum, Isabel and Emily were all graduate students, and then Emily and Peter are at the University of Johannesburg. Okay, so what I want to talk about is two symmetry breaking parameters. And so let me start by just defining those, and then after that I'll talk about a bit of motivation for that. Okay, so the first one is what's called a distinguishing coloring. And for this, what I want to do is, let's say I have some graph, and I'm interested in this one. And I want to place a coloring on the vertices so that when I, yeah, let me actually just do this. So if I do something like this, and then I insist that any automorphism of the graph must also preserve the color classes, by making this vertex orange, now I've sort of taken away an automorphism that we used to have. And so when you have a distinguishing coloring, what you're trying to do is take away all automorphisms except for this trivial automorphism. So, and in effect, you're breaking the symmetry in the graph. So you have some graph, it has some symmetries, and you're saying kind of how much work do I have to put in to take the symmetry away. And so if I go ahead and do this, now what I have is a two distinguishing coloring of this graph. And if I say any automorphism must preserve the color classes, so all of the orange vertices must go to orange vertices, all of the white vertices must go to white vertices. Now the only automorphism that remains is the trivial automorphism. Okay, does that make sense? Okay, so definition by picture.
So you're talking about the color, right?
Yeah, I'm talking about the coloring, but what I'm interested in, there are a couple things you can be interested in. For distinguishing coloring, in general, you're interested in the number of colors used, and you're trying to minimize this. So for this graph, this is a two distinguishing coloring. And for any graph, I'll say that the distinguishing number which I'll just denote by D of G, is the minimum number of colors needed for a distinguishing coloring. Okay, so for this one, I would say that the graph is too distinguishable because I can find a distinguishing color in those two colors. Okay, and then this was introduced by Babai in '77, and then also Albertson and Collins independently. And actually, okay, later, but I don't remember the exact date. Okay, I have '77 written on my paper, which which I know is not right. Okay, so this is one parameter. And then the other one that I'm interested in looking at is what's called a fixing set. And so here, instead of placing a coloring on the vertices, though you can interpret it in that way, I have the same motivation, which is that I'm trying to break the symmetry in the graph. But this time, what I'm going to do is instead insist that certain vertices are fixed in place. So for example, if I place an X here, what I'm saying is that any automorphism must fix this vertex. And then the question is, how many vertices do I need to fix so that, again, only the trivial automorphism remains? And so here, we can do this, and if I say all three of these vertices must be fixed, then I don't have any automorphisms. But one way to think of this, and related to distinguishing colorings, is that this is actually the same as having a color class with only one vertex in it. Okay? And so by saying I want to fix these vertices, it's the same as saying maybe this one is orange, this one is green, this one is blue, and this one is red. And so what I'll say, so yeah, fixing set is a set of vertices such that only the trivial automorphism fixes these pointwise, but I can think of them again in this interpretation. And then the fixing number which I'll denote f of g, is just the minimum cardinality of a set like this. Any questions on that? Okay, and then let me say, this also was introduced separately, so by Harari in 2001 as fixing sets, and then by Deborah Boughton in 2006 under the name determining set. And then this has also been studied with the words rigidity index. So there's a lot of different literature with different names. My preference is fixing set, mostly because distinguishing and determining, it's too many D's, it's too similar. Okay, anyway, so I have these two. I've already hinted that there's a relationship between them, and that the relationship is what I'm interested in. But maybe the plan for the talk, I want to motivate the study of symmetry breaking in general. I want to motivate doing this for trees. And then I want to motivate this question about the relationships between the two. And then I want to answer the question in some way. Okay, so let me put this one up here. Okay. All right, so motivation for symmetry breaking. Okay, so maybe the first thing is to say that you can find the distinguishing number or the fixing number of a graph, or you can bound it even if you don't know the automorphism group. So usually when you're saying or looking at how much symmetry a graph has, the natural thing to do is to look at its automorphism group, maybe look at the size. But it's not always the case that you can do this. And so there are many results where you're finding these parameters, but where you don't know what the automorphism group is. So let me say that, so you can find or bound the distinguishing and the fixing number without knowing the automorphism group. Or if it's not well understood. Two, it's also the case that graphs with the same automorphism group, so maybe you do know what this is. They can have different distinguishing numbers and different fixing numbers. So the study of this is contributing something different in terms of symmetry besides just what the automorphism group is. And then lastly, when you're considering the graph isomorphism problem, understanding what actually breaks the symmetry is related to designing algorithms that are efficient in determining which graphs are isomorphic. Okay, and so like I said, what I'm interested in though is relationships between the two, and then finding a setting for investigating this. So let me say a couple of obvious relationships. Okay, so the first is that if you have a fixing set, you can do exactly what we just did, which is to take every vertex in that set, give it a unique color, and then color the remaining vertices something else. And so you can bound the distinguishing number with this fixing number. So you can say that the distinguishing number is bounded by the fixing number plus 1. And this bound is tight, but these can also be arbitrarily far apart. Okay. And then separately, or conversely, you can also use a distinguishing coloring to bound the fixing number. And so if I have a distinguishing coloring, let's say just with 2 colors, I can look at the complement of a largest color class, and what remains is a fixing set. So in this top example, right, the white vertices are the larger color class. Is that right? Yeah. Yes.
Same side.
Are they? 2, 4, 6 versus
Oh no.
5.
No,
Yeah.
actually.
Yeah. Okay. They could be the same side. Okay.
The
But
root is white, right?
yeah. Yeah. But okay. So yeah. So basically, I can say, okay, these white vertices are the largest color class. Let me take the complement of that, and then I have a fixing set, which is yeah. So. Yes.
So the orange vertices.
Orange vertices.
Yeah, the orange vertices. Yeah, and it's not, okay, yeah, to be clear, it's not necessarily a minimal fixing set, but it is a fixing set. And then, so this is a 2 distinguishing coloring, but you can have d-distinguishing, whatever you want. And so in that case, you're taking some largest color class and you're looking at everything else. So that everything else could be like a set of orange vertices, a set of green vertices. So this could be really large. So what I guess I'm hinting at is that this isn't a good bound, but it is a bound. Okay. And I mean it can be tight in some cases, but I'm trying to motivate that I want to look at this further because I want to find something better than these sort of more obvious relationships. So let me say the fixing number is bounded by the complement. Let me just write this out, what it is. Complement of a largest color class in a distinguishing coloring. And again, the bound is tight, but these can also be arbitrarily far apart. So what I want is something better than this, but in order to do that, I need a setting that's not just general graphs. And so the setting that I want to look at is trees.
Can I ask you a question?
Yeah.
So in the definition of this distinguishing number,
Mm.
we only allow to color only the orange colors, or can we use more?
You
the
can
first
use
one
more
or
colors.
Then this relationship, the first relationship, then why do we need this additional plus one?
I guess so if so for this you want to take some fixing set,
Yeah.
and then I can color everything in that a different color if I want. It's not necessarily most efficient or best way to do this.
Right.
And then I need some other color for the remaining vertices.
Ah.
Yeah. So okay.
Every vertex need a color.
Yeah, let me say like, I mess up on that actually like all the time. Okay, so something else I'm interested in is sort of like the range of what can happen. So let me jump way ahead to the end. But yeah, so when you're talking about distinguishing coloring, what you're doing is minimizing the number of colors used. But you can also say, well, I want to minimize the number of vertices that are receiving a new color. And so when you're doing that, it turns out that this is best possible, but you can also ask what happens along the way. So in this example, doing this, here I'm using 5 colors, but actually and up there I was using 2. If I had just allowed 3, then what I could have done is maybe made this red. I don't need this extra orange, and now I've only changed the color for 4 vertices, but I'm using 3 instead of 5. Okay, so there's, okay. There's a lot of questions related to this too. So as you increase the number of colors, what happens, and sort of when do you get to, this is the number of things you're changing the color of. Okay. All right, so let me go over here. And so let me say something about some recent results on trees that are related to symmetry breaking. Okay, and the first is that actually there's a nice algorithm for finding the distinguishing number on trees. So this is Ching in 2006. Has n log n complexity for finding the distinguishing number. And then also in 2006, Irwin and Harari looked at the fixing number of trees and have an explicit formula for this. And they also showed that you can always find a minimal fixing set consisting of only leaves in the tree. And then the last result I want to talk about is, so when it comes to distinguishing number, it turns out it's often the case that the distinguishing number is 2. And so special interest is placed on this class of graphs and characterizing graphs in this class. And so in 2018, Alakani and Sultani looked at trees with distinguishing number 2, and we're able to characterize all trees with radius less than or equal to 3 that have distinguishing number 2. also give necessary conditions for trees with distinguishing number 2 and radius higher than 3. Okay, and so what we wanted to do, again, is consider relationships between the two and say, okay, in the setting of trees, suppose I know one of these parameters, can I say something about the other? Okay, and so what we were able to show is that if T is a 2 distinguishable tree, of order at least 3, then the fixing number is bounded above by 4/11 times the order of the graph. Yeah. Oh, not intuitive, right? However, you might notice that this graph is 2 distinguishable, has 11 vertices, and we only needed to fix 4 of them. So the bound is tight, and this is one example that does this. And I'll say we also looked at this for d-distinguishable, d greater than 2. The bound there is not as interesting, but I'll put it anyway. So say if the graph is 3 distinguishable, right, and I have this star, and I need 2 of the leaves, and say I have some star on n vertices, I need all but 1 of those in a fixing set. And so when it's d-distinguishable, your bound is just d minus 1 over d plus 1 times the order of the graph, with this being the tightness example. And I will say, too, actually the proof follows very similarly to this, so maybe, and this is the more interesting case, so I'll just talk about this one. Okay. And so for this, the first thing we did was to just sort of start with a base case and say, okay, suppose I have at most 1 high degree vertex, then 4/11 is the bound. Okay, so maybe I'll just write this. And so here I have T is 2 distinguishable. The order of T is greater than or equal to 3, and T has at most 1 high degree vertex. And by this I mean a vertex of degree 3 or greater. Then its fixing number is bounded by okay. Okay, and so once I have this, then now I want to consider any tree. And so let me draw a picture of what happens and kind of what the interesting cases are for this. And so let me say too, intuition for this at first was to take a tree and sort of break off these pieces that you know are 2 distinguishable and that have this bound. And it turns out that actually didn't work, at least in the sense we were originally thinking. And so what we did, so take some tree that's 2 distinguishable. So maybe I have something like this. Okay. And then maybe one thing that can happen is you can have these sort of asymmetric pieces in here that you need to worry about. Okay, so I've got something like this. And so what I'm looking for in here are sort of smaller structures that are two distinguishable and then have these high degree vertices. Okay? But I don't care about all the high degree vertices. So in particular, I don't care about the root. What I want is a high degree vertex that has paths leading up to it where the endpoint is a leaf. Okay? And so I want to sort of collect these in groups, anything that has this property. So this and this. Okay. And then what you'll notice maybe is that not every vertex is in one of these, and that's fine. Because my plan, well, first I want to claim that all of these are two distinguishable. If my tree is two distinguishable, then all of these have to be. Otherwise, I could just look at automorphisms here. And I'd have something, you know, that's, if this part is three distinguishable, then the whole tree would be three distinguishable. And so then it also, I know from Irwin and Harari that I have a fixing set that's consisting only of leaves. Okay? And so what I want to do is look at each of these pieces individually. So all of them have at most one high degree vertex. All of them are two distinguishable. And if the order is greater than or equal to 3, then this base case lemma applies. And so I'm able to take some vertices in here, and in particular, less than 4/11 of them, and I can fix them, and then claim, okay, this piece is fixed. This piece is fixed. This one has order less than 3. This one is asymmetric. And so I fix this part. And then the reason I do this here is, so normally when I'm considering this piece on its own, I'd say, okay, it's asymmetric, so fixing number is 0. I don't need to fix anything. But here I actually do want to fix it just in case there's something that looks like it here. And so I'll just select a leaf, and I'll fix one from each. And what I'll observe, so this we already know is less than 4/11. So is this. And here, if my piece is asymmetric, then it has at least 7 vertices. So if I fix one of them, I'm still within that bound, so it's fine. And then the only thing that's remaining is this, but you can argue that that still is fixed just by the location that's in on the graph. Okay, and so then what I can argue from here is that I fixed all of these pieces. All of them are within this bound, and so when I put it all together, I've been able to fix less than 4/11, the total number of vertices.
In the beginning, how did you break up the tree? You delete the root, or
No, I leave it, but I just don't worry about it. So, yeah. Yeah, so what I'm looking for are these high degree vertices. So a vertex of 3 or more. And I wanted to have a path where the other endpoint is a leaf. And so here, and so they're all of, so yeah, take any leaf in your tree, then it's going to go into one of these high degree vertices.
oh, I see.
Yeah. So you can find and collect them all, and then consider what happens in each of these pieces. Okay. Okay. Other questions? Okay, and then yeah, like I said too, it works very similarly when you increase the distinguishing number, and so yeah, so I guess so the idea here, given the distinguishing number, given that it's a tree, now I can say something about the fixing number. Okay. All right, and so, okay, so now, yeah, like I said, if I have the distinguishing number, I can say something about the fixing number. But now, okay, so in trees, maybe my next question is then what else can I say about the distinguishing number, because now I can see that it's useful for bounding the fixing number. And so let me say too that this question was also motivated by this paper from Alakani and Sultani. And you'll come back here. And the motivation came from the observation that, so they looked at two distinguishable trees with bounded radius. And when the radius was 2, 1 or 2, they actually just listed all of the trees that satisfy this two distinguishability and bounded radius. And so the largest, based on order of the graph, the largest such tree was this one. But what you'll notice is that this tree is inside here, right? Here. And so this was actually our co-author Peter Dankleman's observation, which is to say, to look at this list of all the trees that they had and observe that actually all of them are a special kind of subtree of this larger one. And so, yeah, so something else that we looked at is this question of whether or not that's always the case. So can you find a tree with a given radius such that, and yeah, so some d-distinguishable tree given radius is every other d-distinguishable tree a subgraph of that one? And the answer is yes, but it's a kind of special subgraph. And so maybe, yeah, let's look at this. So this is what we call the universal tree for two distinguishability and radius 2. And it turns out that the kind of subtree I want, so if I just remove this, I'll consider all of these on their own as branches. And then when I'm looking at two distinguishable trees with radius 2, I'll have a root, and then I want some collection of these branches, and I'm going to take the whole piece of it. So I can't just, take this and then not have this, right? So what I'm saying is I need all of these pieces, and it turns out that any two distinguishable tree with radius 2 or 1 can be found from this universal tree. Let me say this is not if and only if though, because if I just take this one on the end, then what I have is this, which is 3 distinguishable. But if I do have a 2 distinguishable tree with radius 2, then it is one of these special subgraphs of this universal tree. Okay, so maybe this here. So the other thing that we were able to show is that there exists a universal tree T of radius r such that if S is a d-distinguishable tree, then S of radius r, sorry. Then S is a, let me just call it a special subgraph what I mean by special is it's one of these that has the root and then these full branches. And then a consequence of this also is that the degree of something like this has been bounded by its distinguishing number and by its radius.
By function of d, like so maximum you mean maximum degree, maximum degree,
Yeah.
some exponential function.
Somewhat.
No, what kind of function?
Oh, actually, great question. I don't know. So, yeah. Okay. Yeah, so we actually just proved that these trees exist. And yeah, maybe I'll say something. Yeah, I think I have the time, so I'll say something about another kind of tree. But we actually didn't calculate like how many of these branches there are, because it gets quite large and quite unmanageable. So it's basically like you're just putting into this everything that you can that maintains the distinguishability. And so like when I go up to radius 3, I can like have this whole thing in there as a branch, and I can have all these branch subgraphs of it as a branch, and I can have multiple copies of them. So I mean, if anybody's interested, I have a picture and I can show you, and it's large and yeah. Okay. But I'm happy to. Okay. Okay. And then. So one last thing of interest as well kind of goes back to what we were talking about earlier, where instead of considering the minimum number of colors, you're looking at the minimum number of vertices that need to receive a new color and sort of what goes on there. Okay, so let's see. Yeah, so actually, okay, so I can define what's called the cost or the paint cost of d-distinguishing. And this is just the number of vertices receiving a new color. Okay? And actually, I should say, okay, when a graph is too distinguishable, this is the definition. When a graph is d-distinguishable, there are a couple different ways to look at this. So one is exactly what I just said. So the number of vertices receiving a new color, and that is from about, I think in 22. But Al-Haqqani and Soltani, somewhat recently, defined it in a different way, where instead of saying what are the number of colors receiving, or the number of vertices receiving a new color, instead you're saying how many, if I'm d-distinguishable, how many vertices am I away from being d-1 distinguishable? So in that case, you're looking for the size of a smallest color class and saying, okay, if this wasn't here, then I could have been d-1 distinguishable, and so that's also of interest. But the one I'm interested in is this one. And so this is the number of vertices with a new color or a special color. Okay. And then this is denoted row with the number of colors of G, and here C is number of colors. And so for this graph, I would say, okay, let me not write the G. So the cost of 2 distinguishing is just 1, 2, 3, 4, 5. And we know the cost of 5 distinguishing is 4. And then you have this question of sort of what happens in between. Okay?
So what do you mean by new color?
I mean the ones like the orange and the green. So yeah, so I think about my graph as having sort of, I guess, all white vertices in this case. And now when I have a distinguishing coloring, I'm placing new colors on them.
Oh,
Yeah, so for this one I mean the orange color. Here I mean orange, green, blue, and red. Okay, but okay. But one thing with this graph is that instead of doing something like this, I could have done had this one be blue, and now I have 3 colors, and I only have 4 vertices receiving new colors. And then in this paper, what was shown is that actually if you have the cost with some number of colors, and I increase that by 1, then the cost with the new color is less than or equal to 1 fewer. So as you add colors, either you're doing better in terms of cost or you're staying the same. And so here we can add this in, and that would be 4, and maybe, okay, now this one is green. And so, yeah, so here, what we can see is that as soon as I introduce a 3rd color, now I've minimized the number of colors, or the number of vertices receiving new colors. And so for any graph, you can actually ask, like, when does that happen? There are also cases where actually this cost, so yeah, this is sort of the full range of this spectrum, where you need at least a distinguishing number of colors, and at most this fixing number plus 1 colors. And so you have this whole spectrum where you're kind of interested in what happens along the way. And then of interest is, yeah, like, when does this occur? This is what's called the frugal number. So when does this cost equal the cost of just using the fixing number plus 1? But you can also, of interest too, actually, is when is this just all equal? And so where, like, you're not helped at all by adding more colors. You can just minimize the cost using the distinguishing number. And then so let me say too, so for that case where the costs here are equal, there also exists a universal tree, and so we have that as well. So so there's a lot of graphs have this property, but characterizing them is of course wide open. And then another thing of interest is, like, so there's at some point maybe, so this could just be like decreasing the whole way, or it could just be equal the whole way. But yeah, if there's equality sort of somewhere on the middle, where is it? And then also maybe, like, so you have this cost with the fixing number, you have this cost with the distinguishing number. At some point, you have some cost that equals this, but kind of what's going on up here, I also don't know. And so maybe, like, you could have something where, I don't know, the cost is like 10, 9, 9, 9, 8, 7, I don't know if something like this exists, actually. Okay. So there are a lot of questions on here. In terms of, like, just looking at the spectrum and what could happen. Okay, but I think Yeah, and I guess I should say also too, so I did look at this spectrum with some of my collaborators from Soka that I haven't mentioned here. So that's John Marzell, San Mobile Mufunda, and Anna Barber. But okay, I think I'll stop here.
Any questions? Tony? Yeah.
So people here like to think about tree width. Have you, does some of this stuff work for just bounded tree width, like the algorithm, or?
I actually don't know anything about tree width, so maybe. Yeah.
Are the numbers here always decrease by 1? So
No.
Oh.
Oh yeah, actually, yeah, I don't know. Yeah.
Will there be a jump up 2?
I don't know. Yeah,
Oh.
actually, I have no idea. Maybe. So yeah. Yeah, I don't know. So I think actually quite surprisingly, so the cost actually, people were only looking at the cost of 2 distinguishing, mostly because a lot of graphs are 2 distinguishable, and you know, I guess the way that it came about is Imrich asked Boughton kind of, well, okay, you have all of these graphs and they're 2 distinguishable. Can you distinguish between those graphs? And the way to do it was to then look at the size of this color class, like the orange color class, and say, you know, how big is it? And then it was a surprisingly large amount of time later when actually the question of, okay, when you have something that's more than 2 distinguishable, then what's going on with like the cost of having the colors? So yeah, so that's brand new, and then like even asking this question, I think we submitted our paper like last spring, so it's also new, and so people haven't been looking at kind of what happens in terms of the cost as you do this. Yeah.
So is symmetry breaking in your title different from the one in physics?
In what?
I mean, the symmetry breaking in your title is different from the one used in physics, right?
I'm not sure.
Okay.
Yeah. But actually, yeah, maybe I'll say one other thing too. In terms of both of these parameters, and a lot of just symmetry breaking parameters in general, the results are looking at just this, or just this, or and something, maybe it's a class of graphs, or maybe the radius or the degree is involved, something like this. Or maybe, you have some class and you find the distinguishing number, and then you find the fixing number, something like this. But looking at them both together actually is kind of rare, which I find surprising, because there are other results with other symmetry breaking parameters where you are considering, how does one impact the other, things like that. Yeah.
Maybe this is not so closely related to your talk, but I just wanted to understand more about these numbers. So are there any some upper bound on these numbers in terms of the size of automorphism groups?
Yes. So yeah. Okay, yeah, the short answer is yes. If you know the automorphism group, then you can say something about these parameters. But you can also know the automorphism group, but then have different distinguishing numbers and different fixing numbers. And so it's not saying everything. Maybe I'll say your life is easier if you know the group. But you don't have to, and it doesn't tell you everything.
In the first theorem of this book, is there any similar result when we replace tree with forest?
Oh, great question. Not yet. No. Maybe. I would guess it's just the same.
Component.
Yeah, exactly, yeah.
Mm-hmm.
Yeah.
Are there any results similar to these besides trees? Maybe calligraphs, something like that?
Not that I know of. Yeah, so actually, I really don't think there's much on knowing one and what can you say about the other, with the exception of the sort of obvious bounds. There's, I think, a few others, but I think the answer is no.
And for your theorem, when you have a universal tree, you mean that this universal tree also has distinguished number.
Yes, I do. Yeah, I realized I
Right.
didn't write that. Yeah.
But otherwise, I could just take some.
Usually that's what universal means.
Uh-huh.
Yeah, normally it should be part of the class you're looking at.
Yeah. There
Yes.
might be some other
Yeah,
approximating.
It comes from category theory.
Oh,
It's a universal object in the category,
Uh-huh.
so it should be in the category.
No, but I did realize somewhere when I was like on a different thing, oh, I didn't write D for that. So I didn't push down. Yeah.
You mentioned that there is a polynomial algorithm finding the distinguishing number of a tree, and is this algorithm also gives a distinguishing coloring? And the second question is, if it is true, then is it isomorphism invariant?
Is it, sorry, the last?
Isomorphism invariant? Since you, at the first you said that it can be used for graph isomorphism testing, and if it is isomorphism invariant, then you'll be very good.
Actually, so I don't know. I don't know much about the algorithm itself. I just know that it exists, but I am happy to send you the paper if you'd like.
Trees, I smoked them. It's easy. Alright, any other questions? So, if not, let's thank the speaker.